quite correct. Two things. The first one is the practice. I had a talk with Lodewijk. So your practices were marked to actually have the correct order in which the links are discovered. Yes. So I asked Lodewijk to adjust his scripts and to remark, okay? To ignore the order in which the links were discovered. He will do that. We'll take the spreadsheet with the old mark and the new mark, and we'll take the max of the two. Is that in order? Yeah? Okay. Good. Mr. Bauer, are you around? No, one of the ghosts. Okay. And the other issue is Mr. Celia asked me, no, he's not here, but I sent him an email anyway. We talked about Dijkstra's shortest path algorithm on Friday, and that will be in the test, right? Juffrou Coetzee, you've got to send me the list of propositions, right? Okay, right. So we talked about Dijkstra's shortest path with the assumption that links are ineligible if it misses that if statement, distance to W is greater than distance to V plus E dot weight, right? Plus the weight of the edge. That concerns the eligibility. If that test is false, the link is ineligible. But Dijkstra adjusts this standard solution to look at 3 vertices. So when going through that example in the textbook, I stressed the fact that we look at non-tree vertices, and I looked at the priority queue with this sort of thing in the back of my head. Yes, of course, you all now know as a link is ineligible if I don't get it, if it falsifies that if, right? So Mr. Celia came up with an added weight somewhere, and the example didn't work out. But if you look at that ineligibility and you change the example as he suggested, then it still works out fine. Yeah, okay? So just make sure that I made an implicit assumption that you all get the sort of weight thing and then concentrated on Dijkstra's non-tree vertices. That's why I kept on saying that link is, or that node is already in the tree, and so on and so forth. Okay. So the priority queue and the ineligibility of the link is not as closely related as you might have deduced from my explanation. Okay. So just look carefully again. The whole thing about shortest path is this ineligibility of a link. And that's all to do with is the distance to the next vertex bigger than the distance to the start node plus the weight of the edge. Okay, good. So I will post, as soon as Ms. Coetzee sends it to me, I will post the propositions that you have to know for Friday. As usual, the proofs constitute anything, normally about 5 out of 30, so round about there. So it's not negligible. If you want to, if you did badly in some of the previous tests, memorize the 4 bloody proofs. Yes, it's not that much. Okay, if you're a bit unsure of yourself. As before, the same hints. Know the algorithms, be able to apply the algorithm to a practical example. Know the time and space complexities. That's about it. Yeah? Okay. And as usual, Thursday morning is your study period. But even in spite of the test, we have to continue. So we are starting chapter 5 today on string sorts. Now, if you think back to project 1, I had the explicit question in the report, which data types did the best as far as sorting is concerned, right? And the strings in general, I think a few people had bugs, but the strings in general did badly in comparison to, for example, the integers. Yes? And we have to look at the reality that almost all practical applications in the real world that you can think of concern strings that you want to sort. Yes, so we can't have very fancy sorting algorithms, and when we apply them to strings, they actually do badly. You also have to, so we're going to look at strings specifically. We're going to look at how Java implements strings and ask ourselves, should I rather use a character array instead of the built-in type? Because a string is definitely not a primitive type. Right? So we don't know what Java does behind the scenes with a string. Okay? It is also important when you move to another programming language, because it's nice if you learn how to program with Java, because you've got this whole library of things and you can program on a fairly high level, but you do have to realize that in other languages where you don't have that high level of abstraction that you can employ, things may look differently. Okay? So we want to keep that in mind, and that is why we specifically look at strings. Okay? And the other thing was, when we measured the time complexity of strings, we looked at two things. Time complexity of strings, yes, okay, it's 9 o'clock on a Monday morning. Time complexity of sorting algorithms on strings. We looked at two things. We look at compares and exchanges. All right? And as you can imagine, if I look at the low level of a string implementation as a char array rather than a string, the compares and the exchanges can somehow become issues. Yes, it's not like an integer that you swap. It's a whole array of characters that you have to swap. So what chapter 5 does for you is it gives you sorting algorithms on strings that do not do compares. Okay, so let's look at this. Okay, Monday morning, 9 o'clock. You should all look at me as if I'm crazy, okay, which I am, but even more so. So we're going to look at two different approaches. The first approach is called an LSD string sort. This is not an April the 1st joke. It really is. It stands for least significant digit. It's got nothing to do, how old are you? Nothing to do with Lucy in the Sky with Diamonds and that kind of thing, right? So it's a least significant digit string sort, yes? Do you like the oldies? I love the oldies. And then the other one is a most significant digit string sort. Think for a moment if you want to sort names. Yes, and you look through a telephone book, you start with the most significant digit. The most significant digit meaning the first one in the string. Okay, because I know if I have the names Yanni, Sunny, and Pity, I know that J comes before P and P comes before S. So therefore, that will be the order, and I'm already finished sorting by just looking at the first character, the most significant digit. But there are cases where it makes sense to start from the back. The difference between the LSD and the MSD sorts is that LSD look at fixed length character strings. Okay? For example, in the good old days before we had personalized number plates, you could think that, no, it's not. No, it's not. If a student number were characters, or if you had a password system, you write your own web server somewhere which requires a password for login, and you restrict the logins to an alphanumeric characters, ASCII set, of 8 characters exactly. Yes. Then I have a string of fixed lengths. LSD works on strings of fixed length exactly. All the keys must have on which I sort must have the same length. With MSD, the keys can have variable lengths. Okay, so there are applications where the fixed length thing works. But in general, suppose I work on surnames, then it won't work. So then we look at variable length keys. Okay. Both of these methods are based on something called key indexed counting. And wait. Before we get to key index counting, 2 other important things that I have to note is the first one is the alphabet and the size of the alphabet. Both LSD and MSD depends on the size of the alphabet. The smaller the alphabet, the better it works. In which case you should jump up and down and say, well, I've got 26 letters. Okay, well, I wanted more than that. For example, in the password case, I want the whole ASCII character set, which is 256. And then you should be happy 256 is not such a big number. Oops, but what did we forget? Extended ASCII, or even worse, Unicode. Yes, why do we need Unicode, by the way? Do you know that? Yes.
Different languages?
Yes. If you want to have Arabic on your keyboard, Japanese, Mandarin. If you want a sign language keyboard, for example, suppose you want to handle Braille. Yeah, ASCII is not good enough. Okay. Braille is very interesting. I actually had a couple of years ago, the first year project was a translation between Braille characters and the normal ASCII, 26 ASCII characters. Anyway, why do we need Braille? What is this woman talking about? Braille, 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 Braille. Do you realize that for a deaf person whose first writing language is Braille, that you get Braille keyboards, right? Blind. I don't think you should take anything I say today seriously. Clearly, I'm still... So they started charging for coffee in the department. And I got my coffee bill for last month. And now I stopped drinking the coffee in the department because I'm a cheapskate and I get an academic salary. And so I'm not awake. But please put your hand up if I talk nonsense. Right. A blind person, yes, uses a Braille keyboard, right? Okay, so there are situations where these alternate input alphabets are very useful, okay? So you may think 26 or, 10 times worse, 256 characters is what you work with. It does not work in the case of Unicode. And Unicode is what you want to do. Incidentally, if you want to do it, if you have spare time and you want a useful additional subject, please do Mandarin. Very useful, very useful. China is simply one of the bigger players in the computer science industry these days. And that little label on your CV will get you a great job. But anyway, in a forward-looking company. Okay, right. The other thing that we want to look at, so that's the alphabet. But if we have an alphabet with restricted size, we could, in principle, translate our character string into integers, right? Okay. So keep that in mind. And now we will start doing key index counting, which is actually very easy, but the book writes it to my Afrikaans heart in such a difficult way that you have to read and read and read and reread, and what the hell. They're taking a very simple thing and making it complex, I think, personally. So this is the idea of key index counting. Suppose I have a list of names, and then I have a second key, which is a small integer. Very important, this must be a small integer. For example, suppose I have my class list. One of the things I always do in the beginning of the year is I take my spreadsheet and I sort according to program name. Yes, so I'm enrolled for a BSc Polymer Science, or I'm enrolled for BSc Computer Science, I'm enrolled for BSc Maths, and so on, because I want to know what the distribution of the class is. So I want to know how many of you are doing computer science major, how many of you are going to have difficulty because the applied maths and the computer science assessment dates are very near to each other, and so forth, right? So if you think of a program as a numeric key and it's a small integer, then that is something that one typically does, right? So this example has input on a name. You'll see that this is already sorted. And then you get a section number. Whatever section may mean here. And the idea is that I want to sort this stably. I want to sort in a stable way to sort the sections. What does stable means? It means that if in the original input something is before the other, it stays that way. It's like sorting in an Excel spreadsheet. First column A, then column B, then column C, or whatever. Okay. Stable sort. So what I would want is, if you look at this input, is cool. So I would start with Harris 1, Martin 1, Moore 1. Yes, Harris, Martin, Moore, they 1, Anderson 2, Martinez 2, and so on. Okay, right. So my sorting is on a key, which is a small integer. Yes, and it is stable. The whole thing about LSD and MSD are that these are stable sorts. If you break that, it doesn't work anymore. Okay? It has to be a stable sort. Right. And here, how are we going to do it? This is a 4-step process. If you look at the test for last year, you will see one of the questions was, name the 4 steps in LSD sorting and describe each one. Okay? You have to know what the 4 steps are. So here are the names. The first is we compute frequency counts. What that means is that I'm going to count how many incidents of there is of each of the keys, right? So for example, the first thing I'm going to do is I'm going to count how many ones are there. 1, 2, 3. Now I know I have 3 ones. Then I count how many 2s do I have. 1, 2, 3, 4, 5 2s, and so on. Okay. I'm going to count what is the frequency of each of the keys that I want to sort on. How many times do they occur? Right? Then what I do is I transform the counts to an index. If I know how many of each counts there are, and I want to store in an array, right? So think of an array. This is very easy. 0, 1, 2, blah, 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 minus 2 and minus 1. If I know that I have 2 occurrences of a certain index followed by 3 occurrent index keys, 2 occurrences of a key followed by 3 occurrences of the next key, clearly the first one must come in the beginning and then the next one. So basically what I do in step 2 is I say, where will my index start for the next batch? So if we leave the 0 open, you'll see why later on. So if my first key starts there and I have 2 elements with that key, then clearly the second key will start at position 3. Yeah, makes sense. I'm pushing them into the array. Yeah. You with me? Okay. Then there's a step called distribute the data. So if I know that when I sort, I will have 2 elements there and then 3 elements there. Basically, I have to put the elements in. That means distributing the data. So we will declare an auxiliary array, okay? And I'll copy the data. Yeah? I'll make sure that I know where each element is. Okay? And then lastly, I copy back the data to the original one. So basically, I calculate for each element where is it going to come in the final array. So let's do this step by step. Let's see if the gray is more visible. I don't know. Can you see that Java there? Should I rewrite on the board? For I equals, it's a 4. I hate 4. For I equals 0. I can't even read it. I less than n, I plus plus. Yes, this is step 1. What I want to do is I want to build up an array called count, because step 1 says count the frequency with which each of my keys occur, right? There's 2 1s, there's 5 2s, there's 5 of these, and so on. Yes, so I'm going to store those values in an array, which I call count. Okay, so count. My original data is in A. Yes. And remember that A contains a name and a small integer key. So what I want is I want to count how many times AI, what is the value of AI.key, and then increment the corresponding element in count. Okay? One line in Java. So just note that we're going to ignore 0. Yes. So over here, we put in a +1 because we're going to start our values at 1. Okay, so let's do it for this example. Right, sorry, that's too quick for myself. I declare an array count. This is my data. I declare an array count. What I want to have is, for the moment, we're going to leave element 0 as a 0. So what I want to know is how many times does each of these integers occur, and I write the answer in the count array. Okay? But it's a +1. So Anderson is key 2, so then it's count 2 plus 1, which is count 3, must be incremented by 1 because I got 1. Example of that. Brown is a 3, so element number 4 is incremented, originally 0, so that's a 1. Then I get another 3, so that 1 is incremented and I get a 2. Okay? So what am I doing? Look at this. What am I doing in terms of sorting? I am going through the data once and I'm updating the frequency counts. Yes? I did no comparisons whatsoever in any way. I simply accessed the array and I went through this once. Now this should let you sit up straighter and forget all the things you are tweeting to the outside world, although I hope you're tweeting that this is one of the best sorting methods you ever heard about. I am not making any comparisons. And what is more, I'm going through my data once. Can you remember the time complexity for the good sorts? If I remember correctly, the best sorting algorithm we had was quicksort, n log n. I'll tell it to you since it's a long way ago, chapter 2. N log n is the best we had really for sorting. I'm giving you n over here, which is an improvement. And that is on string sorts. Okay, so now I have a count array. Okay. I also want you to just think about complexity for a moment here. If I have n elements, right, I'm clearly going through the elements once, but although I am not doing compares, what am I doing? I'm doing array accesses, right? So how many I have there? 2? Did I hear a 2? Wrong. What are you missing? The bloody Java ++. I hate ++. Remember what ++ means? X ++ means x equals x plus 1. So ++ gives me 2 references. Yeah? Just be careful. So I have actually 3 n array accesses there. If you don't believe me, go try it out. Okay, so now I have the frequency counts. What am I going to do now? The next step, this is more visible, right? The next step is to transform the counts, which I now have an array, in an array count. I want to transform those to indices. What indices? I want to transform the counts to something which will tell me where to start each batch, if you want, of keys. Yes, so the first batch starts at 1. There are only 2 of them, so the next batch starts at 3, and so on. Yes? Does that make sense? Everybody happy? Yeah. So let's do it. My Java code for r equals 0 up to the length of the alphabet. Remember, big R is the alphabet size. So we stick with ASCII for the moment, but remember that this is humongous if we do Unicode. Okay. do the following. Let count R plus 1 become a chord Java, because this again hides array accesses. Count R plus 1 plus equals count R. What am I doing? I'm counting. I know how many things there are. Yes, so on the previous page, the final values of count were 0, which is always 0 there in the first position, then 0, 3, 5, 6, and 6. Yes, that was our initial frequency count. So what we now want to do is, given the frequency count, find the index. Okay? So this is always 0. Okay? And this is my initial value of count there, 0, 0, 3, 5, 6. Okay. So what I want for each one is the number of keys less than this value. There are no keys with value 0. Therefore, the number of keys less than 1 is 0. There are 3 keys with value 1. Therefore, the number of keys less than 2 is 3. Yes, because there are 3 ones and 0 zeros. And basically, we're adding. Yes, we're exactly adding. We're counting up the frequency counts. So I know that originally I had 5 in 3, so 3 plus 5 must be added to get 8. So this is cumulative. I go through the count array once and I add cumulatively. 3 plus 5 is 8, yes. 8 plus 6 is 14. 14 plus 6 is 20. Okay. Yes, so that is the position where I start. I have 3 ones. I have 5 3s. Can you see this? I have 3 of these. I put them there. So the place where I start the next lot will be 3 on, and so on. So then I have 3, say, plus 5, which gives me position number 8. So the counts are transformed to positions, to indices. Okay. How many array accesses? Because I'm not doing any compares. I haven't done any comparisons whatsoever. I just counted. Yes. So now I have my indices where the things start. So what I'm going to do now is I'm going to take my auxiliary array, yes, and I'm going to look at where must I put my final value, okay? So suppose this is my count array as it stands. Where's 5, which is 20? My word. Okay, all right. So what I'm doing here is I'm going to say, if I hit a name and a key, I want to know where am I going to put that value in the final array. Okay. And this is the first time that I hit the key 2, so that must go to position number 1, 2, 3. That must go to my auxiliary array in position 3. Yes, because the first 2 that I get. That makes sense. See? There's my unsorted list, there's my sorted list. Anderson 2 goes to position 3, 0, 1, 2, 3. Yeah? Right. So basically, I take my frequency count and I do the copy. Yes, to the aux array. So this is the original input. This is A of I. And I copy that to the aux array. See, aux of count I dot p plus plus is AI. Now wait a minute. If I have something like that, how do I know that the next 2 goes to 4. I know that because I keep increasing my positions in the original count indices. So the moment I hit a key and I do a copy, I increment the index position where the next one of that key must go. Yes? Right? And after that, I copy the whole thing back to the original array. There is my whole sorting algorithm. My sorting algorithm used no compares in any way whatsoever. It used sorting to sort. That makes sense. Yeah. I did not do any comparisons, but I did do array accesses. So we have to count the array access, and the array access clearly is dependent on these 4 loops. This is n times something, this is r times something, this is n times something, and n times something. So it is a constant factor of n plus a constant factor of r, which to my mind sounds linear. Yeah. So we have a linear sorting algorithm which sorts by doing no comparisons. I think it's cool. Okay, so let's just count. And the final count is key index counting uses 11n plus 4r plus 1 array accesses. They, please note that included in this is that they count the initialization of the arrays. So they say, I have to take the array and initialize it. Okay, and that counts as 1. Right? So, initializing takes me n plus r plus 1, the first loop over here. For each of the n items, increments a counter for each of the n items, so that means I go through my data once. Yes, and we just had this big frown on why this is 3n and not 2n. Okay, but I'm still convinced this is 1, this is 2, and I have the plus plus, which means. If you do the assembler next semester, this might convince you better, because plus plus feels like I don't actually do the array access, but you do, because plus plus is just a Java abbreviation for do the array access, do something to it, write it back to the array. So plus plus gives me 2, not 1. Okay, for this one, clearly, I do 3r again, because I have the plus plus, 1, 2, and I have the plus equals, so it's 3, yes. The third loop, over here, I have 1, 2, 3, 4, 1. Let's start again. Let's start from this side. This is one array access. AI.key is the second one. Count is the third one. Orgs is the fourth one, and note that I'd use the plus plus there, so that's the fifth one. Okay? 5 array access, 5n array access in the fourth loop uses data moves. Okay, but in order to move the data, I actually have to access it. So I have to copy the value that's currently in orgs at a certain position to AI. Okay? And Bob's your uncle. Right? That's LSD. Sorry. That is key index counting. What do you have to know for key index counting? For key index counting, you have to be able to name the 4 phases. You have to be able to describe each phase. You have to be able to apply it to a short data set. Okay? 3 or 4 elements. You have to know the characteristics of key index counting. I don't know, I lost my words. Maybe I had a stroke overnight or something. Yeah, key index counting. Key index counting. What are the characteristics? I am sorting in a linear fashion. You have to know that proposition, by the way. Ms. Coetzee marks that proposition, please. Proposition A. I'm sorting in a linear fashion without making any comparisons, but it only works on short integer keys. Yes? Happy? It's cool. Okay. Right, so that is key index counting. So what we're going to do now is we're going to say that if we have fixed length keys. Oh, yes, my thanks for me. Fine. Okay. I'll quickly give the background, but we'll do the detail on Wednesday. LSD string sort works like this. If you have fixed length keys, and it's very important that it must be fixed length. If you have fixed length keys, you can apply key index counting from the back to the front, least significant digit first, and you do that for the length of the key in a loop, and that sorts your data. So what LSD says is, start at the back, work towards 0, yes? So this is the least significant digit, yes? I start at the back, W minus 1. W is the length of the key. I start at the last digit. I do key index sorting only on the last digit, yes? Then I increase my D value, so now I look at the second last digit. I do key index counting again, and for the next digit, and the next one, and the next one, and so forth. Okay. It's deeper than you think. The question immediately becomes, why can't I do this from the front? Why doesn't it work if I do this from the front? Is the first issue that you have to think about for Wednesday. And the second issue that the textbook does try to stress is this works only if the sort is stable. Why is that the case? Well, if I sort on one digit, I have to keep the relative positions of the items for that digit. And then I sort the next and then the next. The other thing you have to ask yourself is the best case and the worst case. We'll do that on Wednesday. If you have questions about the test, please feel free to email me. Okay? I'll see you on Wednesday.